You interact with data every single day. It's behind the websites you browse, the apps you use, those business reports you run, maybe even the smart stuff in your home. Data drives,
Yeah.
well, pretty much everything.
It really does. And if you need to understand that data or work with it or maybe design systems that use it, there's one language you almost certainly need to know about: SQL.
Right, structured query language.
Yep. And it's not just for database programmers anymore. Not really.
Mhm.
For anyone who's navigating tech, dealing with information systems, or just, trying to pull coherent answers out of piles of data, SQL is fundamental.
It's kind of earned that nickname, hasn't it? The lingua franca of data.
Because it really is how we primarily communicate with databases. It's the main tool.
But I think for those of us who aren't maybe knee-deep in code every day, SQL can still feel a little opaque. Just a bunch of keywords sometimes.
Yeah, I get that.
So our mission in this deep dive is to peel back those layers a bit. We're going to trace SQL's journey, which is actually pretty fascinating, from just an idea to a global standard.
And explore why those kind of frustrating dialects popped up between different databases. Why the same query might not work everywhere.
And definitely tackle some really persistent myths that, frankly, influence how people think about data systems, even if they don't write the code themselves.
Right. We've dug through articles, research, stuff that lays out the history, the standardization process, and how it all plays out in the real world.
The goal here is for you listening to walk away not just knowing what SQL is, but really understanding its power, its adaptability as a standard, so you feel, completely comfortable when it comes up in technical discussions.
Exactly. Give you that conceptual grounding.
Okay, let's dive in then. Like any good story, we probably need to start at the beginning. Where did this whole idea of talking to data like this even come from?
Yeah, you got to rewind to the 1970s. Before then, databases were, well, pretty rigid.
How so?
They were often set up in these complex structures, maybe hierarchical, maybe network-based. And to get data out, you had to write pretty specific code that knew how to navigate those predefined pathways.
Oh, okay. So you had to know the exact route beforehand.
Kind of like following, specific physical roads to find a piece of information. It was complicated, not very flexible.
Right.
Then in 1970, this IBM researcher, Edgar F, had a really breakthrough idea. He published a paper proposing the relational model.
The relational model. Okay, what was the big shift there? What was the core idea?
Codd basically said, let's simplify things a lot. Forget the complex, hard-coded links between data records. Let's organize data into simple, intuitive structures, tables.
Like a spreadsheet, rows and columns.
Exactly like a spreadsheet. Each row is a single record, like one customer, one product. And the columns hold the different pieces of information, the attributes about that record: name, address, price, whatever.
Okay, simple enough. So a table of customers. Each row is a customer, columns are name, address, city.
Precisely. And here's the crucial part. Instead of complex pointers linking things, Codd proposed that tables could be linked together just by sharing common values.
How does that work?
Like having a customers table and an orders table. You link them using a customer ID column that appears in both tables. The value of the customer ID connects a specific customer to their orders. Simple values, creating these really powerful connections.
That does sound much more elegant. So that was the theory.
That was the theory. And IBM saw the potential. So in 1973, they kicked off the System R project at their research lab in San Jose.
And this was the big push to actually build something based on Codd's idea.
Yeah, an ambitious effort to build a real working database system using the relational model. System R was the test bed.
Okay, so they're building this new kind of database. They need a way to talk to it, right, to ask it questions.
Exactly. They needed a language. And that's where Donald Chamberlain and Raymond Boyce came in. As part of the System R team, they developed a language they initially called SQL.
SQL, Structured English Query Language. I mean, the name says it all, doesn't it? Trying to make it more like asking a question in English.
That was precisely the goal. Make it more intuitive than writing code to navigate pointers. Just state what you want.
But SQL didn't stick, did it?
No. Turns out there was a trademark issue with another company, Hawker Siddeley, I think. So they had to shorten it to the name we all know now, SQL.
Ah, the birth of the three-letter acronym. But System R wasn't just about the language, was it? I gathered they built some other really key tech, too.
Oh, absolutely vital stuff. Stuff that made relational databases actually practical. Patricia Sellinger developed the first cost-based optimizer.
Okay, cost-based optimizer. What does that do?
It's basically the database's brain. It looks at your SQL query, the question you asked, and figures out the most efficient way to actually go get that data from the tables.
How did it figure that out?
It considers things like, are there indexes available? How big are the tables? How is the data actually stored on disk? It weighs different possible plans and picks the cheapest one, meaning the fastest one.
So you tell a database what data you want,
Declaratively, yes.
and the optimizer figures out the best how. That sounds critical for performance.
Game-changing. It's a huge part of what makes SQL declarative. You state your goal, the system figures out the execution. And another piece, Raymond Loewy created a compiler that could save these optimized query plans.
So it wouldn't have to figure it out every single time.
Exactly. If the database sees the same or a very similar query again, it can just reuse the saved plan. Super fast. These optimizer and compiler innovations were just as important as the SQL language itself for making relational databases competitive.
Right. Theory from COD, IBM's System R, building the prototype with SQL and these crucial performance pieces. But IBM wasn't the only game in town, right? Other people saw this potential too.
They certainly did. Most famously, perhaps, Larry Ellison's company. It was originally called Relational Software, Inc., but you definitely know it today as Oracle.
Ah, Oracle.
They also started developing their own relational system based on COD's ideas and the publicly available research from System R.
And they actually beat IBM to the market, commercially speaking.
Yeah, that's a really significant bit of history. Oracle shipped the first commercial SQL database back in 1979.
Wow, okay.
IBM followed fairly soon after with their own commercial products based on the System R work, like SQL DS in '81 and the really influential DB2 in 1983. So there was this early race to get products out there.
And as these different companies, Oracle, IBM, others starting up, built their own SQL systems, even using System R as inspiration, they started diverging, adding their own features.
Exactly. That's where the concept of dialects really begins to take root. Each vendor built their system slightly differently. Maybe they optimized certain things, maybe they added features they thought their customers needed, maybe they interpreted parts of the early concepts differently.
Okay, but that sounds like it would cause problems pretty quickly.
Oh, it did? A query written for Oracle might just fail on DB2. Or worse, it might run but give you a slightly different result. Yeah. So if you wanted to move your application from one database to another, big headache. If developers had to learn the quirks of multiple systems, also a headache. It hindered portability, created learning curves.
Which points directly, almost inevitably, towards the need for a standard.
Precisely. The industry quickly realized that for SQL to reach its full potential, to be truly portable and powerful, there had to be some universally agreed upon rules, a common language.
And that's where the standards bodies come in, ANSI and ISO.
Yes, exactly. The American National Standards Institute, ANSI, and the International Organization for Standardization, ISO. They took on the job of formalizing SQL.
When did the first real standard emerge?
The first major one was published by ANSI in 1986, technically called ANSI X3.135 1986. ISO followed very quickly in 1987 with an identical standard, ISO 9075.1987. People often just refer to this first one as SQL 86 or SQL 87.
And what did that first standard actually define? Was it comprehensive?
It was foundational. It defined the core concepts, the basic syntax for creating tables, create table, the fundamental commands for manipulating data, select, insert, update, delete, and some standard data types. Think of it as establishing the basic grammar.
A baseline.
The baseline, exactly. There was a minor revision in 89, SQL 89, which added things like integrity constraints.
What are those?
Rules you can put on your tables to ensure data quality and enforce relationships. Things like defining a primary key, a unique identifier for each row, and foreign keys, which are used to link tables together reliably, like ensuring an order always links to a valid customer ID.
Okay, so building blocks for data integrity. But our sources really emphasize SQL 92 as being the big one, the game changer.
Absolutely. SQL 92, sometimes called SQL 2, which came out in 1992, is considered a massive leap forward. It really forms the foundation of what most modern database systems still support today. I mean, the spec itself was something like 5 times larger than SQL 86.
5 times. Wow. Okay, so it wasn't just minor tweaks. What were some of the huge additions that made SQL 92 so pivotal?
One of the absolute biggest, which really improved clarity and reduced errors, was formalizing the explicit join syntax.
Inner join, left join those.
Exactly. Inner join, left join, right join, full outer join. Before SQL 92, combining data from multiple tables was often done using older syntax, primarily in the where clause, which could be ambiguous or lead to, well, unexpected results if you weren't careful. SQL 92 made the type of relationship you wanted between the tables crystal clear right in the from clause.
Okay, so connecting data became much more explicit and presumably safer. What else did it bring to the table?
It introduced richer, standardized data types, things like proper date, time, and timestamp types, and varchar for variable length text strings became standard.
Better ways to handle common data.
Yep. And more robust ways to enforce data integrity, like unique constraints to ensure no duplicate values in a column, and check constraints to enforce custom business rules directly in the database, like saying a price must always be greater than 0.
What about handling complex operations, like multiple steps that have to succeed or fail together?
Standardized transaction control. That's commit and rollback. This ensures that a series of database changes are treated as a single atomic unit. Either they all happen or none of them do. Very important for reliability.
Makes sense.
And crucially, SQL 92 standardized the information schema.
What's that?
It's basically a built-in set of views like virtual tables that let you query the database about itself using standard SQL. You can ask, what tables exist, what columns are in this table, what indexes are defined, what constraints are there.
So, a standard way to understand the database's own structure.
Yes, this was huge for interoperability. Database tools, reporting software, they can all rely on the information schema to understand the database they were connected to, regardless of the vendor.
So SQL 92 really fleshed out that basic SQL 86 grammar into a comprehensive toolkit for serious relational database work. It became the common language everyone aimed for.
It really did set the benchmark.
But you mentioned the standard keeps evolving. It clearly didn't stop in 92.
Not at all. Since SQL 92, the standard has been updated fairly regularly, 99, 2003, 2006, 2008, 2011, 2016, 2019, and most recently 2023. Each revision adds new capabilities, usually while maintaining backward compatibility.
And critically, as you hinted, it hasn't just added more purely relational features, right? It started branching out.
That's a key point. SQL has expanded its scope significantly beyond just tables and rows.
Okay, let's touch on some of those big shifts. SQL 1999 or SQL 3, what was that about?
SQL 1999 marked a move towards what's sometimes called an object-relational model. It introduced features more common in programming languages, like user-defined types, type inheritance, and triggers, which are basically bits of code that automatically run when data changes, like updating an audit log when a row is modified.
And didn't recursive queries come in around then?
Yes, that was a huge one in SQL.1999, the with recursive syntax for common table expressions, CTEs. This allowed you to write queries that could traverse hierarchical or graph-like data structures stored in tables.
Like org charts or parts explosion.
Exactly. Perfect examples. Before recursive CTEs, asking something like, show me everyone who reports up to this VP directly or indirectly, or list all the components and subcomponents needed for this product, was incredibly difficult, often requiring complex procedural code outside of SQL. SQL.1999 let you do it in a single, albeit complex query.
So SQL was getting more powerful for complex logic and structures. What about SQL.2003?
SQL 2003 brought major advances for analytics and data warehousing. The headline feature was window functions, using the over-R clause.
Window functions. What do they let you do?
They let you perform calculations across a set of table rows that are somehow related to the current row, like calculating running totals, rankings, rank sales reps within their region, or moving averages without collapsing the rows like a group E by Y does. Incredibly useful for reporting and analysis.
Ah, okay. Keep the detail, but add context.
Precisely. SQL.2003 also added the merge statement, often called upsert. It lets you efficiently insert a row if it doesn't exist or update it if it does, all in one go. Very handy for synchronizing data. And it started standardizing how to handle XML data within SQL.
Which SQL.2006 then formalized.
Right. SQL.2006 added a whole new part to the standard, Part 14. SQL XML, defining specific functions and data types for storing, querying, and manipulating XML documents directly within the database.
Okay, then SQL.2011 added temporal features, time travel.
Sort of, yeah.
Yeah.
It introduced standardized support for managing time-varying data. Features like period for and system version tables allow the database itself to automatically track the history of changes to your data.
So you could ask, what did this customer's address look like last Tuesday?
Exactly. Without you having to build complex manual history tracking tables yourself, it's really powerful for auditing, regulatory compliance, and historical analysis.
Wow. Okay, we've gone from basic tables to hierarchies, analytics, XML, time travel. What about SQL.2016? This sounds like it was a big one for embracing data types that were becoming popular outside the traditional database world.
It absolutely was. SQL.2016 made a major move to integrate with JSON. JSON had exploded in popularity, especially with the web APIs and NoSQL databases.
Right, everyone was using JSON.
So SQL.2016 added extensive standard functions, something like 22 new optional features dedicated just to JSON for generating, parsing, querying, and validating JSON data within SQL, even if that JSON was just stored as plain text.
So you could shred and query JSON documents using SQL.
Yep, JSON object, JSON array, JSONable, JSON array is JSON, whole suite of tools. It also added row pattern recognition using match recognize, which is cool for finding sequences or patterns in ordered data, like analyzing stock price movements or sensor readings.
So SQL wasn't just adding niche features, it was actively building bridges to handle the semi-structured data people were actually using. What came next? SQL.2019.
SQL.2019 added support for multidimensional arrays, or MDAREs. Think scientific data, weather simulation outputs, geospatial grids data that's naturally organized in 3, 4, or more dimensions. This standardizes how you can store and query that kind of data directly in SQL.
Okay, getting pretty specialized there. And the latest standard, SQL.2023, this one sounds like it doubles down on JSON and adds something really, really different.
It does. SQL.2023, which was finalized just last year, has two major headlines. First, building on the 2016 work, it introduces a native JSON data type into the core standard.
What's the difference between that and the functions from 2016?
The 2016 functions mostly worked on JSON stored as text, like varchar or glob. A native JSON type means the database can store the JSON in an optimized binary format, parse it only once on insert, validate it properly, and build specialized indexes on elements within the JSON documents. It should mean better performance and correctness.
Okay, native JSON, big deal. What's the other headline?
Property graph queries, specified in new Part 16 of the standard, SQL PGQ. This is arguably the most radical addition yet.
Graph queries in SQL, how does that work?
It adds syntax directly into SQL that allows you to treat your existing relational tables as if they represent a graph nodes and edges with properties, and then run graph-style pattern matching queries against them.
Can you give an example?
The syntax looks something like mass.ch, p person dash no rows q person, where p name Alice, you're literally drawing the pattern. You're looking for a person node p connected by a nose edge to another person node q.
Wow. So you can leverage graph database concepts using familiar SQL syntax on your existing tables. That sounds incredibly powerful for analyzing relationships and networks.
It really aims to make graph querying a first-class citizen within the SQL ecosystem. These latest additions, JSON and graph, really underscore a point made in our sources. Modern SQL is vastly bigger and broader than its purely relational origins.
Yeah, I remember seeing a quote suggesting relational stuff is only maybe 20% of the modern standard.
Something like that. The standard is enormous now, organized into many parts, reflecting literally decades of evolution and absorbing new ways of thinking about data.
It's amazing how it's adapted. Okay, so the standard defines this huge, evolving language, but we still live in a world with database dialects. MySQL has its quirks. PostgreSQL does things one way, SQL Server another, Oracle another. How do these dialects fit in with this massive standard?
Ah, yes. The perennial tension between the standard and reality. While the NCISO standard provides that common baseline, every major database vendor implements the standard to varying degrees and, crucially, adds their own proprietary extensions and functions. That's what creates the dialects.
But why do they do that? If there's a standard, why not just stick to it perfectly?
Well, there are a few key reasons. History is a big one. Many of these databases started development before the standards were mature or comprehensive, so they developed their own ways of doing things.
Legacy features?
Legacy features, exactly. Then there's competition and innovation. Vendors want to differentiate themselves, so they add unique features they think give them an edge or solve customer problems faster than the standards process can.
Like performance optimization.
Yeah, performance is another driver. They might tailor syntax or add functions specifically optimized for their underlying database engine architecture. And sometimes they just implement features. Users are clamoring for years before those features make it through the sometimes slow-moving standards committee process.
Right, so it's a mix of history, trying to be first with features, and genuine technical differences.
It is. The key thing for portability, though, is that most dialects do support a substantial common core of the standard. Your basic select, insert, update, delete, create table, that stuff is usually pretty consistent.
So simple queries often work across different systems?
Often, yes. But the moment you start using more advanced features, specific functions, procedural extensions, or vendor-specific utilities, that's where the differences really bite.
And for someone listening who isn't writing SQL day in, day out, why is it important to be aware of these dialects?
Because you'll encounter them. Maybe you're looking at a report definition, or you're involved in a discussion about migrating data between systems, or even just choosing which database technology to use. You might see syntax or hear about features or limitations that are specific to one particular dialect.
So understanding that the same idea might be expressed differently is key.
Exactly. The same conceptual task, getting the current time, combining strings, handling missing values, might require different syntax or even behave subtly differently across systems. Knowing that dialects exist helps you ask the right questions.
Can we look at a couple of quick practical examples from the sources just to make it concrete? Like, how do you get the current date and time? Seems simple.
Simple task, but varies. Standard SQL defines current timestamp. You'll see that work in many places. But in practice, you'll very commonly see NULL or Notorious used in MySQL and PostgreSQL. In SQL Server, it's often getDate, or the more precise setState time. In Oracle, it's traditionally susState.
Single, different names. Okay. What about sticking text strings together? Concatenation.
Standard SQL uses the double pipe operator. PostgreSQL and Oracle generally follow this standard. But SQL Server historically used the ++ for strings, like you might in some programming languages, though newer versions also support a standard concat function. MySQL primarily relies on the concat function.
Okay, minor syntax differences. But let's talk about the one the sources really flag as a major point of confusion and difference, handling NOL.
NOLL, yes. This is where dialect differences and just understanding NOL itself can cause real problems if you're not careful.
So conceptually, what is NL again? It's not zero.
Absolutely not zero and not an empty string either. NOL represents an unknown value, a missing value, or maybe a value that's simply inapplicable for that particular record. It means we don't know or it doesn't exist.
And Standard SQL has some tricky rules around comparing things to NL.
Very tricky
Yeah.
and crucial to understand. In Standard SQL, comparing anything to NOL using regular comparison operators like NaOL, etc., results in a special third logical value, unknown. Not true, not false.
So where my column equal doesn't work.
It will never find rows where my column actually is NULL, because the comparison yields unknown, which fails the where clause condition. The standard correct way to check for NL is using ISNL or is not NL.
But some dialects try to help with this.
Yeah, some add non-standard operators. MySQL, for instance, has the operator the NL safe equals, which will treat two NLLs as equal. But relying on that makes your code non-portable and can mask the fundamental concept.
Okay. And how do functions that summarize data like SUM or AVG handle NL?
Most aggregate functions, SUM, AVG, MIN, max, STD, DV, simply ignore NL values entirely when they do their calculations.
So if you're averaging salaries and some are NLO, they just don't count.
Correct. They're excluded from both the sum and the count used to calculate the average. This is usually what you want, but you need to be aware of it. Counted is different. It counts all rows. But count_mt column name only counts rows where that specific column is not NLL. Getting the right count is vital.
And the sources mention one really specific notorious difference between dialects regarding NULL, something about empty strings.
Yes. The big Oracle difference. In Oracle database, an empty string inserting into a varchar2 column, their standard text type, is treated exactly the same as NELL. They are indistinguishable.
Wait, really? An empty string just becomes NLL?
In Oracle, yes. But in almost all other major databases, PostgreSQL, SQL Server, MySQL, SQLite, an empty string is treated as a distinct value, a string with 0 length. It is definitely not the same as NELL, which means unknown.
Why does that seemingly tiny difference cause so many problems?
Oh, it has huge implications.
Exactly.
Data validation. If you define a column as not NL in PostgreSQL, inserting it's fine. In Oracle, it will fail because Oracle converts the null to NELL, violating the constraint. Querying. If you want to find rows with blank information, do you search for ISNELL or column? The answer depends entirely on your database dialect and how the data was inserted. And migrations. Migrating data between Oracle and, say, PostgreSQL is a notorious pain because of this. Blank fields might suddenly become unknown fields, or vice versa, potentially breaking application logic.
That really drives home how these conceptual differences, often rooted in dialect choices made long ago, aren't just academic. They can seriously affect your data's integrity and how your systems behave.
Absolutely. And even for newer standardized features like common table expressions, CTEs using with, or window functions, while the core concept is now widely supported, you might still bump into minor syntax variations or differences in the specific functions or options available in each dialect.
So the standard provides the blueprint, the common language foundation, but the dialects are like slightly different regional accents and slang spoken in the various database houses. You need to be aware of them.
Well put.
Okay, let's shift gears a bit. We've talked about the standard and the dialects. Now let's talk about how SQL and these database concepts actually play out in broader system design discussions. Because the source material brought up several really common misconceptions, myths almost, that seem to crop up again and again.
Yeah, these are the kind of things you hear in architecture meetings or when people are trying to troubleshoot performance issues. Getting the reality behind these myths is really helpful, even if you're not the one writing the sequel.
Okay, kicking off with myth number one. Joins are inherently slow and should be avoided at all costs. You hear this a lot, right?
All the time, especially when comparing with some NoSQL approaches. But the reality is, joins are absolutely fundamental to the relational model. It's how you're supposed to combine related data that you deliberately separated into different tables to reduce redundancy and improve integrity.
So they're not inherently evil.
Not at all. Performance isn't really about avoiding joins. It's about good database design, having the right indexes in place, running the query efficiently, and crucially, the database's own query optimizer. Remember Patricia Sellinger's work, being smart enough to figure out the best way to execute that join.
So the optimizer's job is to make joins fast.
Exactly. Try to work around joins by, say, pulling huge data sets into your application layer and combining them in code, or by massively duplicating data everywhere, which is called denormalization, can often lead to much worse performance overall. Not to mention making your application code way more complex and creating huge risks of data inconsistency.
Right. If you store the customer's address in 50 different order records and they move.
Nightmare to update consistently. So the real takeaway isn't avoid joins. It's design your schema well, index appropriately, write sensible queries, and trust the optimizer to make joins efficient. Understanding the different types of joins, inner, left, right, full, outer, is about specifying how you want the data combined, which is the right level to think at.
Okay, good clarification. Myth number two. Just index every single column in your table to make everything fast.
Ah, the index everything approach. Sounds tempting, maybe. More indexes must mean faster lookups.
Seems logical on the surface.
But indexing is fundamentally a trade-off. Indexes absolutely do speed up read operations. Select queries using where clauses, linking tables and joins, sorting data with order by. That's what they're for.
Got it.
But they slow down write operations. Insert, update, delete. Why? Because every time you change data in a table, the database also has to update any indexes that cover that data. More indexes mean more work during writes. And of course, indexes take up storage space, sometimes a lot of it.
So indexing everything can cripple your insert update performance and balloon your storage costs.
Precisely. Effective indexing is strategic. You typically index columns that are frequently used in where clauses or join conditions, especially columns that are selective, meaning they have a high variety of unique values, like an email address or a primary key. Indexing a column with only 2 or 3 possible values, like a Boolean flag or a simple status, often doesn't help much. It just adds overhead.
So it's about identifying the critical columns for reads based on how the application actually uses the data.
Exactly. Performance tuning involves thoughtful, selective indexing, not just blindly applying them everywhere.
Okay. Myth number 3. ACID properties are just old school relational database stuff. They're outdated or irrelevant now, especially with NoSQL.
ACID. Atomicity, consistency, isolation, durability. Yeah, you hear this sometimes, often in the context of certain distributed systems that might relax some of these guarantees for higher availability or scale.
But are they really outdated?
Far from it. AC properties are the bedrock of data reliability and integrity, especially for transactional systems. Think finance, e-commerce checkouts, inventory control, healthcare records. Anywhere correctness and reliability are paramount.
Can we quickly unpack what each letter means again, conceptually?
Sure. Atomicity. Transactions are all or nothing. Think of transferring money you debit one account and credit another. Both have to happen, or neither does. The transaction is an indivisible unit.
Got it. C.
Consistency. A transaction must always bring the database from one valid state to another valid state. It must obey all the defined rules and constraints. If you have a rule that inventory levels can't be negative, a consistent transaction will never violate that rule. Isolation. This deals with concurrency, multiple transactions happening at the same time. Isolation ensures that concurrent transactions don't interfere with each other. From the perspective of any single transaction, it should appear as if it's the only one running on the database.
Prevents weird interactions. And D.
Durability. Once the database system tells you that a transaction has been successfully committed, that change is permanent. It will survive subsequent failures like power outages or system crashes. The data is safely stored.
So saying ACID is outdated is kind of like saying data reliability doesn't matter anymore.
Pretty much. While some systems legitimately make trade-offs, for example, using eventual consistency in highly distributed systems where temporary inconsistencies are acceptable, the need for strong ACID guarantees in many core business applications is precisely why traditional relational databases remain so dominant for those workloads. And interestingly, many newer database technologies are now adding stronger consistency options, recognizing the importance of ACID principles.
So ACID concepts are alive and well, and maybe even spreading. Okay, myth number 4. Normalization is always the best way to design a database, or maybe the flip side, denormalization is always better for read performance.
The normalization versus denormalization debate. Another classic trade-off, not an absolute rule.
So normalization first, what's the goal there?
Normalization is the process of organizing your tables and the columns within them to minimize data redundancy and improve data integrity. The idea is to store each piece of distinct information only once. Store the customer's name and address in the customer's table, not repeated in every order's record for that customer.
Benefits.
Reduce storage space, easier updates, change an address in one place, prevents inconsistencies. Impossible to have two different addresses for the same customer if it's stored only once.
Downside.
To get a complete picture, like all the info for an order, including customer details and product descriptions, you often need to perform more joins to bring the separated data back together. This can sometimes impact read performance for complex queries.
Okay, so denormalization is the opposite, intentionally adding redundancy.
Exactly. You might decide to duplicate some data to speed up specific common read queries. For example, in an orders table, you might include the customer city, even though that information also exists in the customer's table.
Why would you do that?
If you frequently run reports that group orders by city, having the city directly in the orders table avoids the need to join with customers every time, potentially making those reports much faster.
What the risk is.
Inconsistency. If the customer moves, you now have to remember to update their city in the customer's table and potentially in multiple rows in the orders table. If you miss one, your data is now inconsistent. It also uses more storage space.
So it's a classic trade-off based on how you use the data, reads versus writes.
Precisely. Systems that are heavily focused on transactions, OLTP online transaction processing, where data integrity and efficient writes are critical, tend to favor higher degrees of normalization. Systems focused on analytics and reporting, OLAP online analytical processing, where complex read performance is paramount, often employ more denormalization in carefully chosen ways, like in data warehouses or marts. It's a key schema design decision.
Got it. Final myth, and this is a big one, especially in comparisons with the NoSQL world. SQL databases don't scale.
Yeah, that's a really persistent perception, but it's largely outdated. It probably stems from the era when scaling a database often meant buying a single, much bigger, much more expensive server, vertical scaling.
But that's not the only way anymore.
Not at all. Modern SQL databases absolutely can scale, and they can scale significantly, supporting huge data sets and very high throughput.
Oh, what are the techniques?
Primarily through horizontal scaling, distributing the load across multiple servers. One common technique is using read replicas. You have one primary database handling writes and multiple read-only copies that can handle the read traffic, spreading the load.
Okay, distributes the reading. What about handling more data or more writes?
That's where techniques like sharding or partitioning come in. You physically split your data across multiple independent database servers. Maybe you shard customers by region or orders by date range. Each shard handles a subset of the data and traffic. It's more complex to manage, but allows for potentially massive scale out.
And the cloud has made this easier, presumably?
Hugely easier. Cloud providers offer managed SQL database services like Amazon RDS, Azure SQL Database, Google Cloud SQL that are designed for high availability and scalability. They handle a lot of the operational complexity of setting up replicas, managing failover, and sometimes even helping with partitioning strategies.
So the idea that SQL can't handle large scale is just wrong.
Largely, yes. SQL is a perfectly viable technology choice for large-scale, high-traffic systems today. The conversation isn't if SQL scales, but how to architect it appropriately to achieve the scale you need using these modern techniques.
That's a really important clarification. It sounds like many of these myths boil down to misunderstanding the design principles, the trade-offs involved, or the modern capabilities and scaling patterns available. The sources also touched on a few other common conceptual pitfalls like we discussed with NLL again, or people using select habitually when they only need two columns, which is inefficient.
Right, fetching unnecessary data. Or another common one is applying functions to columns directly inside the where clause, like where upper last name Smith.
Why is that bad?
Because it often prevents the database from using an index on the last name column. The database would have to calculate UPR, last name, for every single row, and then do the comparison instead of quickly looking up Smith in the index. The fix is often to make the comparison value match the column's format, like where last name Smith, assuming names are stored uppercase, or use function-based indexes if the database supports them.
Subtle things that can kill performance.
Exactly. These are the kinds of things that, even if you're not writing the SQL yourself, affect the systems you use. Understanding them helps you participate in discussions about performance, data quality, and efficient design. SQL's power comes with the need to use it thoughtfully.
Okay, so SQL has been around for, what, over 50 years now, which is practically an eternity in technology terms. What's the secret sauce? What explains its incredible longevity and its continued undeniable relevance today?
I think it really comes down to two things. Its incredibly strong theoretical foundation, that declarative set-based approach rooted in the relational model is just fundamentally powerful and elegant, and its truly remarkable adaptability.
We definitely saw that adaptability tracing the standard's evolution.
Yeah, as we discussed, it hasn't stayed frozen in 1970s relational purity. It has consistently evolved, absorbing new concepts, adding features for analytics, objects, time, XML, JSON, even graphs, all while generally maintaining that core SQL interface.
And it's still absolutely central to today's data landscape.
Undeniably. It remains the undisputed lingua franca for relational databases, which, let's be clear, still power the vast majority of critical transactional systems worldwide. It's deeply embedded in cloud platforms.
And beyond traditional databases, too.
Yes, crucially, SQL or SQL-like interfaces are pervasive in the big data world. Frameworks like Apache Spark, with Spark SQL, Apache Hive, Google BigQuery, Snowflake, they all offer SQL interfaces, allowing data analysts and engineers to leverage their existing SQL skills on massive distributed data sets, often stored in non-relational formats.
So your SQL knowledge transfers.
It transfers surprisingly well, and it's increasingly used in data preparation and feature engineering steps within machine learning pipelines too. It's just a very effective way to select, filter, transform, and aggregate data.
So it seems like SQL is less about being tied to one specific type of database and more about being a universal standard for interacting with structured and increasingly semi-structured data, almost regardless of where or how that data is stored.
That's a great way to put it. It really resonates with a point Peter Eisentraut made, commenting on the SQL.2023 standard, adding native JSON and graph querying. He described SQL as increasingly acting as a bridge.
A bridge between what?
A bridge reflecting the industry's desire, as he put it, to manage more data in more ways, embracing things like JSON and graphs, but doing so while keeping SQL, relational data, and strongly typed schema-organized data at the center.
That makes a lot of sense. You're not throwing away the decades of investment, the skills, the tooling, the robustness associated with SQL and the relational model. You're extending that stable core to encompass these newer data paradigms.
Exactly. It shows that the SQL standard isn't just some dusty historical document. It's a living specification that continues to be shaped by both theoretical computer science and the very practical demands of the real world, adapting to how we actually want to manage and query information today.
So to wrap up, we've really traced the arc of SQL from Edgar Codd's relational idea and IBM's pioneering System R through that crucial standardization phase culminating in SQL 92, and then watching its continuous evolution, absorbing capabilities for complex data, analytics, time, XML, JSON, and now even native graph querying.
And we've looked at the practical reality of dialects, why they exist and why being aware of them matters, and hopefully debunk some common myths around joins, indexing, ACID, normalization, and scaling that can sometimes cloud system design discussions.
Our hope is that this deep dive is giving you, the listener, a richer, more conceptual grasp of SQL. It's so much more than just a list of commands. It's this powerful, incredibly adaptable standard with a fascinating history and clearly a very dynamic future.
Understanding its core principles, the trade-offs involved in database design, the nuances of things like NLL handling, the reality behind those performance myths, we think, that really empowers you to better understand, discuss, and make decisions about the data systems that are all around us.
And thinking about that remarkable history of adaptation, absorbing JSON, absorbing graph concepts, it really leaves you with a provocative thought, doesn't it? Given SQL's proven ability to evolve and incorporate new data models, what new frontiers, what other kinds of data or querying paradigms might SQL set its sights on next? And how will that ongoing evolution continue to reshape what we even mean by a database language and how we interact with the information that underpins, well, everything?
It's a fascinating question. It definitely suggests SQL's story is far from finished.